Welcome to the session of binary search. In the last session, we have seen divide and conquer algorithm paradigm, its general method. Today, we are going to see its application, which is a popular search technique called as binary search. Let AI, where I is within the range 1 to n, be the list of elements that are sorted in increasing order. To solve the problem of determining whether a given element X is present in the list or not, divide and conquer can be used. Let the problem size be 1, then small of p from the control abstraction is true, and in this case, the solution of the problem will take the value I if the element you are trying to search is present at AI. Otherwise, it will take the value 0. In this case, the g of n would be g of 1, which is going to take the time complexity as theta of 1 because only one comparison is sufficient. If the size of the problem is big enough, then we will be dividing the problem into various subproblems by considering a index q. Pick an index q and compare x with the element aq. Three possibilities arises. If the element you're trying to search x is equal to the element present at aq, in this case the solution is found immediately, or if x is less than the element present at aq, in this case x has to be searched only in the sublist ai plus 1, so on to aq minus 1 because we have considered the list to be in the sorted order. Therefore, the size of the problem P reduces to Q minus I, AI plus 1, so on till AQ minus 1, and the element you're trying to search, which is X. The third case is the element you're trying to search, X, is greater than the element present at the index AQ. In this case, the sublist to be searched would be AQ plus 1, so on till AL. And the size of your problem would be L minus Q, and the list A, Q plus 1, so on to AL, and the element you're trying to search. This division takes only theta of 1. If Q is always chosen such that AQ is a middle element, then the resulting search algorithm is known as binary search. The answer to the new subproblem is also the answer to the original problem P. So in this case, we don't require any additional combined function. Binary search algorithm can be written in a recursive manner or a non-recursive manner. Let's see both the versions of binary search algorithm. This is a recursive binary search algorithm. If the problem size is P, then you're going to compare the element with the element which is present in the list. If it is success, you're going to return the index I, else you're going to return 0. If the problem is not small, then you're going to calculate the middle element and you're going to compare the element with the middle element. If it is true, you're going to return the middle position. If not, you're going to check the element you're trying to search is less than the middle element. Then you're going to call the binary search function by making the necessary changes. Else, you're going to call again the binary search recursively by making the necessary arrangements as your lower bound and upper bound. This is the algorithm for non-recursive binary search. As long as elements are present in your list, you're going to calculate the middle element and you're going to check whether the key you're trying to search is present at the middle element. If it is success, then you're going to return the middle position. If not, you're going to compare whether the left side should be searched or the right side should be searched. According to this output, you're going to arrange the lower boundary and upper boundary of the list. If the element you're trying to search is not present in the entire list, then you're going to return the value -1. Example, let the set of elements be shown in the slide. The element we have to search is 21. So first we have to calculate the middle element. So indexes are numbered from 1 to 12. So middle element would be calculated as 1 plus 12 by 2, which is 6. The element which is present at the middle position is 21, and the element we are trying to search is also 21, meaning it is a success. So the position will be returned as a solution telling where the element we are trying to search is present in the given list. If you are trying to search for the element 23, first we will be comparing that with 21. So since 23 is greater than 21, so we know it has to be present in the right side of your list. So we have to accordingly rearrange our lower boundary and the upper boundary to segregate the searching process. From next iteration onwards, the lower boundary would be 7 and the upper boundary would be 12. Again, we are going to calculate the index middle element, which is 7 plus 12 by 2, which is 9. So the element which is present at the 9 is 62. So 23 is less than 62, meaning it has to be present in this left side. So again, we are going to shift our lower and upper boundaries accordingly. So our list would now become 22 and 36, and the indexes would be 7 and 8. So again, you are going to calculate the middle element, which is 7 plus 8 by 2, which is 15. So which is going to give us the index value as 7. So 23 is compared with 22, which is greater, but we don't have element next to it. So meaning the element we are trying to search is not present in the list. In order to understand this in a better way, it is always convenient for us to construct decision binary search tree, which is binary decision tree, taking the values of mid and projecting those values as the tree structure. The node value talks about the mid values we have calculated by using low plus high by 2. So our tree would be like this. So the node value is nothing but the middle element at every positions. So when n is equal to 12, the middle value would be 6. The left side talks about 1 to 5 and the right side subproblems talks about 7 to 12. Again, you're going to calculate the middle element for this list as well as the middle element for this list. So you are going to keep on constructing the tree where the node gives you the middle values. Whenever you cannot calculate the middle value, you're going to represent that with a rectangle node which talks about null. So the same example, whenever we have to search for the key 21, so the first mid value with which you're going to compare 21 would be 6. The value which is present at the index 6 is 21. It is a success. To search for the element 23, so first you're going to compare with the element 21. So we know it should be to the right side. So we will be checking with the next element which is at the position 9. So that element would be 62. So we know we have to visit the left side. The next element with which we have to compare the value will be 7, which is 22. So we know we have to move towards the right. So the element which is to be searched is 36. So we know it should be towards the left, but we have reached the end of the node, which is a rectangle node, which represents the element we are trying to search is not present in the given list. The computing time of binary search would be theta of 1 in the best case, O of log n, and theta of log n, the average and the worst cases when the search is successful. When the search is unsuccessful, the time would be theta of log n. So how the time is derived? So T of n, the equation would become T of n by 2 because we are dividing the problem into two subproblems. And since we don't require any additional time to combine the solutions into a single solution, the time f of n would be 1. So when you solve this equation, we are going to get the time complexity as O of log n. Hope you have understood the working methodology of binary search. For the next class, try to do this assignment. So explain binary search algorithm for the following elements. Construct the binary decision tree and search for the elements -6 and 127. In the next session, we will be talking about merge sort, which is also one of the popular application of divide and conquer algorithm paradigm. Thank you.